So P1 writes and P2 reads, right? So we have to make sure if they are if there is no single write and read, how are we going to manage this? How are we going to synchronize the accesses, right? Because at the end of the day, we don't want to end up in a situation that we have a read after a write or a write after a write. So these are some data hazards in databases also. We refer to a read after, a write after read and a write after write. Okay, so we have to make sure we have set up a mechanism to synchronize these accesses. So normally there is a hardware support needed for this. We call an operation atomic when by doing an operation there is no other operation can be done on that specific segment of memory. For instance, if you want to access a variable using an atomic operation like read or write, right? In a way, your hardware implements a mechanism that doesn't let any other processes to access that variable or change or update the value of that variable, right? So starting from 0 to 100%, when you're done with your work, it's going to be making that specific variable available for other processes. So we call this operation an atomic processes. Think about it as the bank transactions. So all of the transactions in banking system should be atomic. When you transfer some money, like $1 million, right? Say you're rich and you're transferring million and million. So there's no way that transaction would be done in half, right? That transaction should be done completely. So that's an atomic transaction. When you submit that transaction in the banking database, think about it as the lines of your operations. This should be done complete, right? That's an atomic transaction. All right. So let's see how we're going to do that. In RISC-V, we have two methods for that. I mean, we have a load and a store method for that. So we call this load reserve double word. We show that with LRD. And then we have a store conditional double word. So we show that with SCD, right? So by load store, by load reserve double word, we are loading from address in register 1 to the destination of RD, as you see here. We need to have a place for reservation on memory address. We see some examples in the next slide. And on the other side, when we want to store that, we can define it with SCD of RD of the register 1, RS1, and RS2. So what it does is actually storing from RS2 to address in RS1. So what it returns is it's going to succeed if location not changed since the load. So and that's the important part. We don't want that to be changed. Otherwise, we are we are accessing some value that has been altered, right? So the success will return 0 and fails return a non-zero, which is 1 in RD. Okay, let's see two examples of that. So the first one, example 1 on top. So we have an atomic swap. So we want to swap the values of two variables, right? So we're gonna use this load reserved D for x10 and x20, right? And followed by that, we have to use the store operation, x11, x20, and x23, right? And we only branch if we didn't find, if branch not equal, which is the case that x11 was not equal to x0, right? As long as we didn't receive the succeed return, we have to carry on trying, because before that the load was setting that to 1, right? Because we are making sure that there is only a single process access that specific address. after it stopped loading here again and again, the moment it found this to be 0, it's going to access that, right here. So it's as if someone is holding the address, holding that register to itself when it does the atomic operation on that, right? So the first one is actually one to indicate whether the atomic operation failed or succeeded, and one to hold the value to be stored in memory if it succeeded, right? So since the load value, since the LRD, load reserve, returned the initial value, and the store conditional returns 0 only if it succeeds, at the end we can add the I 0 and x10 to x23. Okay, is that clear, the first one?
Can you explain again what is inside X11 register? What is the status? Like it is 0 or 1?
Yeah, some value, yeah. So here you could see that for a store, it's the RD, which is the destination register, the source 1 and source 2, right? So that was the destination. And an RD was here, was getting loaded before.
I don't understand how it is checking whether the location is changed or not.
Which location?
It says that succeed if location not changed since LR.D.
So when the first load was finished doing its job, right, at x20, it's gonna open up, it's gonna set that branch 0, and these two become equal, and as long as they're not equal, you have to try again. It's like you have to wait for the other process to just finish doing the stuff, and then you are able to access that. So we call the over process atomic, right? Because we are swapping the values.
So it is just like a wait counter or something, which is waiting for.
Yes, somehow, yeah. We are sort of putting a sort of a lock, yeah. The example 2 actually does that in a more efficient way.
So in SCD, you're moving the data from X23 to X20. And X11 is more like it's like a Boolean to tell you whether it succeeded or not.
Yeah, that's right. Is that clear? Okay, so let's have a look at the second example, which is we are implementing sort of a lock, which is a more efficient way to perform that atomic swap here. So in example 2, we are trying to acquire a lock at location in register x20, okay, where the value of 0 means the lock was free. So 0 means free, and 1 means the lock was already taken, right? It's locked. Okay. At the end, when we finish this routine, we're gonna unlock that, right? We make it 0. So that's the end part. So say here, we read the lock. As long as it's locked, we cannot do it, so we have to just carry on and again. We wait for that 0. And then here, we can store it using SCD of x11 in register 11 of x20 and x12, right? We attempt to store it if it was unlocked. Questions? There are so many other ways to implement an atomic function, either in high-level languages or in a hardware. Even your OS has some functionalities in that. So perhaps in other courses you're going to see other, definitely in your operating system course, you're going to see some other techniques to do locking. In general, this is called a mutually exclusive operation, right? Because these two operations to be mutually exclusive. Yeah.
So in line second, so it is basically loading x20 into x10, right?
Which one? In a
LRD
annotated again, LRD x10.
Yeah, in read log line. It
Okay.
is basically loading x20 into x10. Then it is comparing that value with x0, whether it is 0.
Yeah.
So is it mandatory to load a 0 value only? We cannot load any other value?
No, it's going to only branch if not equal. So if it x10 wasn't equal to 0, x0, right?
Yeah, for that one, you said you're loading x10 and then you're storing x11. And then if x11 does not equal 0, it goes to again, right? That's right. So what's the point of loading x10 then?
Because you're making sure that you're reading the lock first. If the lock wasn't set, you can read, you can continue. Right? Was that clear? First, you have to make sure it's not locked. If it's not locked, you can just do the store. You don't seem convinced. Just lock and unlock is just two values. We assume if it was unlocked, which is free, it was 0. If it was locked, somebody has already set that to 1, right?
So it's something we define.
Yes, yeah,
Oh,
yeah. Okay? Yeah.
So when you run again, aren't you just loading from the same place over and over again?
Yep. I mean, just for the hope that we find a better, we find another value for the lock, right? By the time we just check again and again, at some point the other set it to 0, right? And then we are able to access that. Yeah. Always thinking about atomic operation as that bank transaction that I mentioned. Okay, so let's just go for the translating a program, starting from the high-level code. Say here is a C code, assume it as any high-level language. Then we are trying to understand the overall process up to it's loaded to memory and it's getting executed. So this is the execution. Right, so that's your program. Let's see what are the steps in between so that your high-level language can get executed in the memory. So what we're going to see here is how the compiler generates an assembly language, right, out of the C program in this case. So you've seen many assemblies so far in the past lectures. Then there is another module in a compiler called assembler. So normally in most of the recent compilers, they have assemblers, linkers, and loaders itself in a compiler. So when we talk about the compilation process, we are talking about all of them at once. I'll show you some examples right after these slides. So your assembly code will get us, using an assembler, it's going to output the objects of the code. Then you need a linker to link those objects with some certain libraries if they need be. And then at the end, you need to execute that, right? You need to load it to memory before the execution. So these are some steps that a compiler does. We're going to talk about it mostly today. Okay? But for now, let me see if I can show you something here. can access here. Okay, let me just share this screen so you can see that over there. Display. Okay, let me just show you an example in Linux. How does it work? So suppose you have a simple hello world application, right? You just want to write load IO. Then you just have an main, and then you just print, right? You say print F. Just nothing. Say hello, and then you return. Okay, very simple code. Is anyone familiar with GCC compiler? So GCC is one of the well-known compilers in Linux and Unix system. There are many compilers you can use. In your Windows, they might have an Intel compiler for that. But using GCC, we can show actually how does the process work here. Okay? So GCC, that GCC compiler accepts your C-level language that we just wrote, right? In one step, if I just write GCC hello C, if it doesn't find any error, so no news is good news, it's going to come up and show me the shell again, right? So with one process, it has output a file here called a.out, right? So that a.out is my executable. If you just check type a.out, I'm sorry, file. You can see file. You can see that this is 64-bit ELF for executable on x64 or x86 machines. So this is an Intel executable, right? Think about it as another architecture that you didn't know. So you're talking about RISC-V. So on Linux devices and on Mac and your computer, mostly you have x86 devices, right? So in one step, it has generated the output for me. If I just run a.out, which is my executable, I'm going to see the output as my hello, right? It's as if that I have from here, right? It just goes down to the executable. My executable is a.out here. Just think about it as your .exe in Windows, right? That's my hello. .c just goes directly to here. Now, okay, I have to look at there now. So now I can use my compiler to guide that instead of just outputting the executable right away, why don't you just output the object file for me? So I can just pass -c, just make it bigger. So I'm just gonna say -c hello. So that's my source file. I'm just going to say output the assembly file using -s as my hello.s. Okay? So now what it does is just, it receives an input, my hello word, which was the high language, and it's going to output my assembly file. Now, if you take a look at the assembly file there, S file, you see it has all the assembly file for the string of hello, the text, the global strings, and all so on and so forth, related to the hardware architecture of the Intel systems, right? So what you do with your RVS is just use another architecture for RISC-V. Okay. So basically, using a compilation framework, you can see all those different assemblies that are getting output. Even you can use, let me just come back here. You can even use XXD that outputs the hex dump of the output. You see, this is all the hex file, the hex dump of my small program that I just wrote, which is just a print hello. Okay? So all these different modules are available at your use. So now today we're going to talk about every individual compilation module. If I find my slides, just here. Okay? So we can go directly from here to there using a modern compiler, or we can just step it into individual levels, starting from the assembly, linking, loading, and so on and so forth. Okay? All right. Let's see, we've already passed the assembly one, and we are up to the point that we are having object module, right? So an assembler, which was inside a compiler, translates program into machine instructions, right? The one that you saw, that you just saw for Intel x86. So suppose this is the, you use another compiler just like your RVS simulator, and it's going to output based on RISC-V, right? It provides some information for you. That information has header, text segment, static data segment, relocation info, symbol table, and debug info, right? I'm going to talk about all of those today. So for instance, a symbol table is going to define a binary version of each of the instructions. An assembler has to determine the address corresponding to all the labels. Okay? So let's see an example of this. So this is a very simple function that has external double bar, which is the name of the function. So a symbol table using that high-level language would be all the symbols used here, bar, which was the name of the function, your variable x, foo, count, and so on and so forth. And for each of them, you have the type and a scope, right? So the compiler actually generates this with the binary format of each of those type and scope for you. As an example for RISC-V, you have this. You have the labels, you have the addresses. Okay? That's part of your symbol table. The rest of them could be the text segment, relocation information, and so on and so forth. Just go on this. Okay. Okay. So after we pass the first assembly, and then we go up to the linking step, now we have to produce an executable image. Okay. At this point, we have to merge our segments. We have to place code and data symbolically in our memory. Then, for this, we have to determine the address of data and instruction labels. Okay? And lastly, we have to patch both the internal and external references. So that's the main three tasks for linking. I have provided the specific functions you can use in GCC if you are interested in applying it at home, if you have a Mac or a Linux machine, or you can even use it in your lab machines here. So the first line it's gonna use GCC, our compiler, right, for the first file with these libraries that we are including, and it's gonna output the first object of the first file as file1.object. Say the code that we're working on has two C files, file1.c and file2.c, right? After compiling this and generate the object, now we can generate a shared executable out of that by using gcc.share, and these two objects that we already generated here, file1 and file2, and the final executable would be called leap.so. Right? This is the share object. I'm going to talk about it. But basically, you can try that at home if you were interested in playing around with the different phases of compilation. Any questions so far? Are you lost? Oh, you're there. Are you worried about the pre-lab, right?
Yes.
Yeah, it's just obvious.
You're not going to ask the last question, right?
What is it?
The last question?
Last question of the pre-lab?
Yeah.
How about the last question about this?
Is it though?
All right. Now, we are up to the point that we have the objects. We want to load a program, right? We want to load that objects into a program. Loading actually works as follows. So first, we have to read the executable header and determine the segment size, right? Both for our data and the text we have. We need to have, we need to create a large enough virtual address space. Then we need to copy those text and data into memory, right? You have to copy all the parameters into the stack. We talked about the stack last session. And then finally, we have to initialize the processor registers and set the stack pointer to the first free location. And finally, in order to run the routine, we need to branch to a startup routine that copies the parameters into the argument register and calls the main routine of the program. So that actually runs the program. So here's an example of an executable file header. And it's going to show actually, after the linker updated the addresses here, right? So we can jump, we can use this jump JAL, and link instruction uses, in this case, a PC relative addressing. Thus, the JAL address at where is this one? Okay, it's going to go to the procedure B, which is this down there. So it's going to start loading that. And after the address was loaded, it's going to use X3 as the base register, assuming it was initialized to the 1000 and the rest are 0 hex. And then it's going to store the address, and it's going to go from X to Y as a double word. Okay, that's basically when an execution works here in RISC-V. So now we can produce two different executable objects or executable file out of that. One, we can include everything that was necessary inside our executable. We call this static, right? And the other one is like we can do that dynamically as a dynamic link library. So if we go with the dynamic version, we only link libraries when they were called at runtime. Because, for instance, assume that you wrote a program that was using math, right? Some math functions, and you were including so many header files and other libraries inside. If you statically produce the executable as a static library, so that library contains all of those included libraries. So perhaps the executable will become a huge file, right? That's one of the downsides. But if you produce a dynamic link library, or what you call in Windows a DLL file. In Linux, we call it so.so file, or a shared object. Only those link or load libraries will be used when they are called at runtime. So that's a major difference between a dynamic and a static library, right? Even with a dynamic linked library, we can apply a method called lazy linkage, and that was the case that only for the first time on the left path, you see that we are finding all those connections between our variables that they were dynamically mapped, right? So we start from here and we go to another jump, and then we find this data and then this text and that text, and we come back to the end, which was the first call to this DLL routine, right? Starting from the next iteration of the code that is running, you don't need to come all the way down because you know what was the endpoint. So you're going to call that from the subsequent calls. So that's the difference between these two. Any questions for now? All right. Now let's see how does a Java program works here. So just like the C in Java, the only difference is instead of a conventional compiler, it uses a just-in-time compiler. A just-in-time compiler or a JIT compiler normally profile the running program to find where the hot functions or hot routines of the programs are, the one that needs to be run more often, right? And then compile them into native instructions while the code is running. So you don't have to spend time for the compilation phase before you run that. It's going to run it when it was needed, okay? So at some point you're going to have some speed up because you don't need to compile the overall program all at once. You just compile those hot functions that you want to use here. All right. So let's see an example now from C, which is a sorting example. And let's see how we're going to run that on RISC-V. So that's a simple sorting algorithm, right? Well, actually, let me see. It's actually a swap. It's not a sort. So let me just swap. So we are actually defining a long int temp, and the temp is defined to be of k, and then we are trying to swap the two value of vk with this vk plus 1, and then we change that vk plus 1 equal to temp, right? So the RISC-V instruction of that would be this. So I'm just going to start from the beginning. So the first step is to get the address of vk by multiplying k by 8, okay? Here. So this is 8. That is equal to 2 to the raise of 3 shifting, right? So that's what is shift left doing here. Now we load the vk using x6, and then vk plus 1 by adding 8 to x6, okay? So you're up to here now. Then we store x9 and x11 to the swap address. So these two. And then at the end, we're going to store the values. After the finish of the routine, we're going to come back first where we were. Okay? Was that clear? Okay. Let's see a bigger one. So a non-leaf routine, which is a sort procedure in E. So we are trying to sort. So we are trying to sort an array. So we have for I equal to 0 and smaller than n, we go one by one. We have another counter. We decrease it by 1 at every iteration. We're going to swap this as long as j is greater than 0 and v of j is greater than v of j plus 1, right? We need to swap it because we're trying to sort that. Okay? So let's see how we're going to implement it in RISC-V. So as you see, we have two loops here. One here for the outer loop, one here for the nested loop inside. Okay, for the outer loop, for the iteration outside, for I equal to 0, smaller than n, I plus 1, we have this. This is the outer loop. We're just gonna check for branches greater than or equal x19 and x11. It's gonna go to exit 1, right? As long as this condition didn't satisfy, it's going to go inside the body of the outer loop. Let's call it the nested loop or the inner loop inside. It's going to add I1 to x19, and then it's going to branch at the end. Okay, so that was the outer loop. Let's have a look at the inner loop. The inner loop was actually doing for j equal to I minus 1. So every time we have to reduce 1 from I, we need to check if first of all, j is plus, is a non-negative integer, and then v of j is greater than v of j plus 1. Okay. Then we need to swap that. Okay. Now let's see what's happening here in the inner loop. So that's the skeleton for that. We use at first a BLT if the condition didn't met, so we go to exit right away if x20 was smaller than 0, which indeed the case that j was negative, right? Otherwise, we carry on. We shift that again by 3, which is equal to 8 here. We add the value to x5 to x10, right? And we save it at x5. We load our two values that we want to swap and check first, right? And then we branch if the case was less than or equal, so of these two. If x6 and x7, we actually trying to implement x6 was smaller or equal than x7, right? Which is vj and vj plus 1. And then if the condition was met, we do the MVs, which is copy parameters from x10 into x21, and then x11 into x22. Is actually doing a swap here for us. And then finally, we're going to reduce 1 from the j, and we're going to add x20 minus 1. We branch to test of the inner loop. So we go back to the inner loop. Okay?
When you're loading register 7, right, and it's equal to VG and then the array j plus 1, right, how come you did LD x7, it's 8, and then in the circle brackets x5? Because, like, wouldn't you have to go to, like, the array itself and then add x5 with, like, another 8 to move it over in the array? And then load that?
So say that again. So Your
so
question
like,
was.
don't you have to like add x5, the register x5, with like 8 to move it over another thing index, and then load that up into thing x7 to actually get like the value that's right.
So if you look at this, the high level code,
Yeah.
so this side. So we are only doing the swap if for the case that J wasn't J was non-negative, right? And only the value of Vj was greater than Vj plus 1. Okay? Otherwise, we just don't do that. Right? So if the condition was met, we just doing the add I minus 1 to J, and then we do the swap. So your question was before this, before the check or after the swap?
It was just like why you did it in the way where you wrote 8 equals, 8 circle brackets x5.
Here.
Yeah.
Oh, your question is why this is 8?
Yeah.
Because here, you remember? Here. Right?
Yeah.
Just like the previous example that we show here. Yes. So the first step also here was to get the address of Vk by multiplying k by 8, right? Vi shift left by 3. Because we can represent 8 by a shift of 3, because 2 to the raise of 3 is going to be 8, right? A shift of 3 is going to get the address of 8. It's going to get the address of Vk, which was the 8 for us. Was that clear?
Yeah.
Okay. All right. Yeah, I can pass this. There are a few slides left on chapter 2. Mostly they are information for your yourself. Like sometimes when we do, let me see actually here. Many of these optimizations that we do, here can be done automatically by a compiler flag, right? And in famous compilers like GCC that I just showed you today, or LVM or Intel ICC, there are certain levels of optimizations. We call it, and they start with -O, like -O1, -O2, and -O3. So each of them are implementing certain level of optimizations towards your code. And these are the results because normally by using a more radical optimization such as O3 or O2, normally your performance will increase. But sometimes your code size will also increase. And that's why, coming back to the notion of performance evaluation in the first chapter, CPI and instruction count normally is not a good, tool to understand the performance. You see, by using O3 on both cases, we have more instruction counts or more CPI. However, the performance was vastly increased by using O3 with respect to the original code, right? You have this amount of speed up. So these are just for your own information if you wanted to have a look. The final thing that I'm going to mention here is the use of arrays versus pointers. Okay, let's see an example of using arrays versus pointers in a function called clear. So you want to clear all the values of your array to 0. Let's see if we implement that using pointers, what's going to be the difference between implementing it with non-pointer values. Okay, so what you see is like two different implementation of the clear. We call that clear 1 for the non-pointer version on the left, and that's the corresponding RISC-V assembly. On the right side, you have clear 2, which uses pointer to do that. So the first one is just you have an array with this. So that clear one accepts 2 arguments. So size of the array and the array itself, and then you initialize I as an int, and you go into a loop, and for all of those i's of your array, you're gonna assign 0 to that. So you're gonna basically clear that array. On this case, you're accepting 2 pointers, a pointer to an array, which is, you call it an array, and also you have a pointer called p. That stars is a pointer here, and then you assign. So let me first of all ask you a question. Do you all know what a pointer is? Have you had your programming languages before the course?
We use Java, so they don't do pointer.
Oh, so you don't know any pointer, right? Who knows what a pointer is? Can anyone explain it in a simple one sentence? Can you explain it?
I was guessing. I was just saying like it was a memory or something like that.
Close enough.
Yeah.
Can you explain it?
Or point to a reference.
So a pointer is a variable that contains the address instead of a value, right? So its value is the address of another thing. So it points to that address. That's what we call it pointer. And the way we show it in high-level language like C is by this star. Like this int C, int a star P is we have defined a pointer which is called P, and it's a pointer to integer, right? So the value of P is an integer address, okay? It points to that address. So there are two ways to just implement that clear function. So what we do here, this ampersand returns the address of the array 0, which is the base address of that array. So that P value has an address inside. So that's your P. I don't know, 1, 2, 3. So that's your pointer P. So you assign the base address of your array to that pointer P, and then you say while your P is equal to the maximum size of that array, which is the last memory address of the array, you just go P plus 1 is as if you're pointing to the first element of the array, and then you go one by one. So that's your array up to the last point, right? But instead of doing it directly, you're using a pointer to point to that, right? It's an indirect way to access things or manipulate things in a high-level language. So now we have two different implementation of one function, and both of them are outputting 0 to all the values of that array, okay? Either we do it directly using arrays itself, or we are using a pointer P to point to the addresses and using that pointer to clear that value up. You see, at each point, the star P is gonna assign 0 to that address of the array that was pointing to. Yeah, I guess it's a little bit difficult for you to understand what a pointer is without any prior knowledge, but I'm trying my best to showcase it, because you need a whole chapter of object-oriented language to understand pointers. Anyhow.
Sorry, are we supposed to translate the C program onto these languages in exam?
Not necessarily a huge program, or I mean, we just want to test how you understand working with RISC-V, you know, the assembly. You don't have to, because it requires a specific course, like an assembly course, to write assembly code. But just small things just like what your pre-labs are asking you, right? Not anything more than that.
So a pointer, you're pretty much saying like a pointer is like a variable that stores an address, right? So in this situation though, like if you go to a pointer and add its address, you just put in 0, right? That's what you're pretty much doing.
So when you do this, you're referencing that, you're accessing the value of the pointer.
Okay.
So a star P is the value that the address of P pointed to, right?
Okay.
If you want to access the address, you just use the ampersand. That's why so you define that pointer, star P, and the value of the pointer is the address of the first base address of the array 0, right? So if you go to P, you print the output of the P, it's going to be the address of the array 0.
Okay.
right? But if you want to access the actual value of array 0, you need to access it using star p again, right? So it's like indirectly you're manipulating your values inside your array. Okay. I mean, it has a whole new world of details, but as a very high-level definition, that's the difference between just accessing directly or using a pointer. Okay. All right. So now, if we take a look at the different assembly generated by clear 1, which was array, and that was a pointer version. So we see that the version on the left must have the multiply and the AND here because of the shift inside the loop, because I is incremented and each address must be recalculated from the new index because we are accessing the array itself from this base, right? Is 0, which is the array 0, 8, 16, and so on and so forth, 8 by 8. However, on the right side, if we use a pointer to indirectly access that, what's going to happen? The memory pointer version on the right side now increments pointer directly. So we are incrementing pointer by pointer. Right here versus here. So in this case, we are saving shifts here. Right? We are saving that multiplication because we are now just doing an addition. P is equal to P plus 8. The other one is like you have to do an I multiply 8, right? And always multiplication is a more computationally intensive operation than addition. Okay? So one of the advantage of pointer in general is like it's going to reduce the instructions executed per iteration, right? In a high-level compiler, sometimes you don't even have to change your implementation of a code. Like in GCC, you can use -FIV Optimization, which is standing for induction variable elimination. So it's going to implement the same effect on your code. All right. The rest of the slides are just some general information about MIPS and Intel x86. So these are mostly for your information. Starting from Wednesday, we're going to start chapter 3. Chapter 2 is over. And I'm going to post some, just like what I did for the first chapter, I'm going to post some sample questions from the book. So just you can work on them. These are very close to your midterm. We don't want to have any more complex questions other than what your book is presenting, right? And I'll try my best to